Okay, hello, welcome everyone. Can everyone see a slide that says Lecture 3, Maximum Likelihood Estimation? Give me a thumbs up yeah. Okay, great, thank you. Um, so yes, the technical setup is slightly changed today. We'll see if we can hopefully avoid some of those technical difficulties from last time, but no guarantees. We'll see how it goes. Mainly, I'm just excited to go back to in-person lectures where these technical difficulties do not arise as often, but let's make the best of this. Okay, so today's lecture is maximum likelihood estimation, but first, because we didn't quite get through it last lecture, I wanted to finish up on some of the math review, specifically the part about vector calculus. So remember, vector calculus is kind of a combination of the things that you've learned in linear algebra and multivariable calculus, if you've taken those classes. Specifically, in this class, we won't talk a whole lot about vector calculus, but over and over and over again, we're going to use these concepts called gradients and Hessians. Gradients mostly, but also Hessians to an extent. So what do these concepts mean? Well, when we have a function that takes as input a vector, so some array of numbers, and then outputs a scalar, so a single number, then we can think about the column vector of partial derivatives of the function with respect to every entry in the vector that we input. And that's what we call a gradient. So on the next slide, I'll actually write out what this looks like in math, but this is a textual definition of a gradient. There's also a concept that's kind of interesting in its own right. It's not quite as crucial for this class, but we will talk about it a little bit, which is something called a Jacobian matrix. And this applies if the function, instead of outputting a single number, a scalar, outputs a whole vector. Because then when we think about partial derivatives, we can think about partial derivatives with respect to every entry in the input as well as every entry in the output. So then that vector that we used to have the gradient now gets stretched out into a whole matrix, and that thing we call the Jacobian. The last concept that we'll use is something called a Hessian. One way to understand the Hessian is that it's the Jacobian of the gradient. And that doesn't make sense. It's worth chewing it over in your head. Perhaps one simpler way to understand it is that, again, if we're going back to the case where our function just outputs a scalar, then it's the matrix of partial second derivatives for that function. And a really useful resource is what's known as the matrix cookbook. You can go see it in the link here. And section 2 has a lot of really useful identities and things like that written out so that you can have it for quick reference. Okay, so let's actually write out some of this stuff. So what was I saying before? Well, what I was saying, right, is that you have some function f, and it takes in, some vector, let's say that lives in Rn, and then outputs a scalar. These are R's. Okay, so this is what's known as function notation. If you've never seen it before, hopefully it's relatively intuitive. Basically, it means that, f is some function that takes in x, where x here is an n-dimensional, let's say, column vector, and it outputs y. Y here is just a scalar. Okay. So when we're thinking about this function f, when we say the gradient, which we denote with this upside down triangle, the gradient of f with respect to its input x, that's the notation, is the following column vector. It's the partial derivative of f with respect to x1. And so that's the first entry in x, our vector, right? All the way down to partial derivative of f with respect to xn. It's this column vector right here. Okay, and just as a sort of a terminology bit, sometimes you'll see the term derivative being thrown around. So not partial derivative, actual like full derivative. And usually people use this just to denote a row vector that's the same as the gradient, but the gradient is usually a column vector. So very commonly, you'll see people write something, oh, I guess I'll write it over here because I'm running out of space. You'll see some people write something like df dx, and this is just the gradient transpose. Why? I actually don't know. it's just common to see something like this. Okay, and then the last thing that we have is a Hessian, right? And so the Hessian sometimes is denoted with a capital H, although I already used that for entropy, so that can get a little confusing. Other times you'll see people write the same symbol, but squared. And remember, this is a whole matrix where we have partial second derivatives with respect to all of the combinations, all of the pairs of entries that we have in our vector x. So the first one will be x1 squared. Right over here, we have something like x1 xn. I'm going to run out of space. xn x1 down here. xn squared. Okay, one thing that you want to note here is that this matrix is square, and it's also symmetric. And for convex functions, this thing is what's known as positive semi-definite, which we talked about last time. Which we talked about last time. It's actually one of the ways to check whether or not something is positive is a convex function is by checking its Hessian. Okay, so that concludes the math review. Are there any particular questions about anything that we've gone over here? Okay, great. Then let's move on to our actual content. Or this is content also. Let's move on to today's actual content. Well, actually, before I do that, I think I forgot to mention an administrative note about discussion sections and office hours. So apologies for the delay on announcing discussions and office hours. As you might imagine, we're still struggling through some things, but we're like 95% of the way there. So what we're going to do, well, actually, if you look at the website already has the discussion worksheet posted. And it also has in the calendar page, the discussion times listed. So what you can expect is that after this lecture, you can go check Piazza and posts about specific discussion logistics like Zoom links and things like that. There will be a post for that. And then there should also be a post about office hours on Piazza after this lecture. So again, apologies for well, I wouldn't say dragging our feet because it's been a little hectic, but certainly sorry for getting this information out a little bit late. But hopefully this week, you can start attending those sections and office hours. They do start this week, by the way. Okay, so today's lecture is going to be about covering one of the main principles for what in this class we'll call learning, right? But in other areas like statistics or like electrical engineering, all these things, they use other terms like fitting, estimating, sometimes even identifying. But we'll call it learning parameters. And what we'll talk about today is pretty generally relevant to all different types of statistical models, not just machine learning models. But obviously in this class, we'll focus on why it's relevant to machine learning in particular. Although in this lecture, we'll sort of introduce it in a more general way. And the principle is referred to as maximum likelihood estimation, which maybe you could guess from the title of this lecture. So in this lecture, we'll first go over the core concepts. So talking about maximum likelihood estimation, or MLE, in a pretty general way, not just specific to machine learning. And we'll provide some non-machine learning examples of what MLE actually looks like in practice. And then in the next lecture, we'll then detail how this principle actually applies in the context of machine learning, and also discuss some connections of MLE to sort of other approaches that we can also think about. So just as a little bit of context, maybe 10, 20 years ago, if you were teaching a machine learning course, you might not start with something like maximum likelihood estimation. And in fact, even today, sometimes people don't. But in the current landscape of what machine learning looks like, this concept of MLE is really quite important, and also quite a good way to understand in a very general and clean way a lot of what machine learning is about these days. And so that's where we're going to start in this class. So let's first recap a little bit about what is machine learning, which is something that we did last Wednesday, if you remember. And here we sort of paraphrase for the purposes of transitioning into what we're going to talk about. So remember that machine learning has kind of these three core concepts or components around it. One is the model, and then one is the optimization, and then the last one is the data. So the model, right, is this function that we learn from inputs to outputs, and it has these parameters that we learn, that we optimize in order to make it in order to sort of make the model define the function that we want it to be. And the optimization algorithm is the thing that actually tries to find or learn those parameters that fit the training data that we're given. The question that we're going to start with is, how do we actually define what it means for parameters to be a good fit? So intuitively, this might make a lot of sense, right? We want parameters that give us a model that accurately predicts outputs given inputs. But how do we actually measure that? And what's the criteria that we're going to use? So what we need specifically is what we call a loss function, which measures how good, or maybe I should say how bad, parameters actually are. So basically, this is going to be a function that takes in parameters and then gives you a single value. The higher that value, which means the higher your loss, the worse those parameters are. And so what we're going to be trying to do is actually minimize that loss function. Okay, so we're going to be looking for parameters that minimize that loss. That's our learning objective. Okay, and so that's how we're going to define this whole machine learning setup, machine learning problem. Okay, so let's take a little look at actually what that looks like. Pull up my notes here. Okay, there we go. So in machine learning, we have our data, right? And for example, if we're dealing with a regression problem like this one, right, where we're trying to regress to real value targets y, let's call this axis y, given some input x. Here, this is one dimensional, but x could be, any number of dimensions. Then the data that we're given are all these blue dots, right? They're like, some number of input-output examples that we're given. And so we'll denote that as a set of xi, yi, where I equals 1, all the way up to, some capital N, which is like the number of data points that we're actually given, the number of examples we're given, right? And then this model that we're trying to learn, remember, is we usually write it as f subscript theta. Theta are our parameters, right? That takes in x and then tries to predict y. That's what we're trying to do here. So what might this model look like? Well, for example, in this example, right, this model is being represented as this line, this red line. How do we parameterize a line? Well, we can say something that looks like f theta of x is equal to, w transpose x plus b. That defines something that's linear in x, right? And then in this case, theta, our parameters are w and b. Those are the parameters that we're trying to learn. How do we fit this line to the data that we're given, right? Now, what we need to do is we need to define a loss function, which tells us for a certain set of parameters, how good are those parameters? Well, one way that we can actually write this loss to begin with is to write it as a function of the target that we're trying to predict, and then the actual prediction that we end up making. So the way that we're going to write this here is to write it as follows. Oops, still have it. Okay, great. I have some loss function, which I denote L. And I'm going to say that L takes in two things. L takes in a target, which I'm trying to predict, so a y value. And then it takes in the actual prediction that I made. So hat here denotes prediction. So for example, if I have a linear model, right, then y hat is w transpose x plus b, right? And for example, in regression, I can make that something like squared error, right? Now, our objective is going to be to find parameters that minimize our average loss. And how do we write that? Well, we say that the best parameters that we could possibly hope for, theta star, is equal to the minimum over all my possible parameters, all possible WB, for example, right, of the average over my training data loss. So the loss here is going to be, this target that I have, yi, and then the prediction that I'm making. So f theta of xi, which again, for something like a linear model is just W transpose xi plus b, right? So specifically for squared error, right, what I end up getting, a lot of the same stuff out here. And then yi minus f theta xi squared. Right, so now that, as it turns out, right, for a linear model, if f theta of xi is W transpose xi plus b, some of you may have seen this in previous classes, or you might just know about it, and we'll also talk about it in this class. This problem is, this minimization problem is actually quite easy to solve if f theta is linear and we're working to try to minimize squared error, right? That's called least squares linear regression. And we'll talk about that, in next lecture and also the lecture after that. Okay, so that's basically what we're talking about when we talk about loss functions and also the learning objective in machine learning, right? So a loss function tells you essentially how good or bad parameters are, and then the learning objective is to find parameters that minimize that loss. Okay, so now let's actually talk about maximum likelihood. So in order to talk about maximum likelihood, the first thing that we actually require is that we need the model to not just output some prediction, not just to output some like scalar y hat or something like that. It actually needs to define a probability distribution over the data. And then we need that this distribution is controlled by the model parameters. What exactly does this mean? We'll talk a little bit in detail on the next slide about what this actually means mathematically, but basically think about it this way. The model is no longer just predicting a single value, it's predicting a whole distribution of what y could be given x. That's basically what that means, and we'll see again an example of what this actually looks like. But it's important that we get this concept to be crystal clear, because we're going to really focus heavily in this course on what we call probabilistic models, which are models that define a probability distribution over the data. And so hopefully on the next slide, this will become a little bit more clear. And then over the course of this course, you're going to see a lot of different examples of probabilistic models. In maximum likelihood, what we're assuming is that there is some setting of the parameters that generated the observed data. What does that mean? It means that we actually think that our model is specified correctly, right? So we actually think that there is a true underlying linear relationship, for example, between the inputs and the outputs. And really all we're trying to do is we're trying to identify, recover what that linear relationship actually is. So there is some setting of the parameters. We don't know what those parameters are, but if we could just find out what they were, then we'd be able to explain our observed data. That's the underlying assumption behind maximum likelihood estimation, or at least it's the way that people usually motivate maximum likelihood estimation. If this is true, if our assumption can hold, then what the maximum likelihood principle says is that we can recover these parameters through optimization by essentially just maximizing the likelihood of the observed data. That's why it's called maximum likelihood estimation. And we'll see in a couple slides exactly how this plays out. But first, let's actually talk a little bit about probabilistic models and what that might actually look like. So there are a lot of different examples of probabilistic models, and it kind of depends on what form, what type your data takes. Let's take an example of regression and see how we might be able to define a probabilistic model. So for example, I had a linear model, right, where I had f theta of x. X here is one dimensional. Let me write it in cursive. Is equal to W transpose, and x is one dimensional. So I could actually just write Wx plus b, right? The transpose would be if I had, higher dimensional data. This was my linear model, right? If I wanted to define a probabilistic model instead, what I could say is, well, actually, maybe what I want to output is not just a single estimate of y, right? Not just w times x plus b. Instead, what I want to output is a distribution over the different possible y values that I could have. So instead of this, for example, I could output an entire Gaussian, right, which I denote with this funny looking n, where maybe the mean is wx plus b, but then there's also some variance attached to this prediction, okay? So what might that actually look like pictorially? Well, so here, right, I have a mean. And so let's take a look at a particular x value. Let's say like, x equals 30 over here on this graph, right? Well, x equals 30, well, what I would be doing is I would be saying, well, here's the mean that I'm predicting. Okay, that's wx plus b, right? But then I also have some type of variance that I attach to my estimate, right? And that variance might look something like this, depending on how large sigma is. And then really what I'm actually predicting here is kind of like, let me see if I can draw this, an entire distribution over different y values, right? Given a particular x value. So I'm saying that, I'm fairly confident that this is the correct average prediction, this correct average y prediction to be making, given this particular value of x equals 30, right? But there's actually, maybe there's noise in this process for how y is generated. We can sort of see that, right? Like not everything falls perfectly on that line. Or maybe there's measurement errors or outliers or whatever else there might be. So I want to encode that somehow into my model. I want my model to say, well, this is a good average value, but we might be kind of wrong here for various reasons. And so I kind of want to encode there's some uncertainty or some stochasticity in the predictions that I make. And so that would be going from a single estimate, right, from a linear model into an actual probabilistic model, where here we call this a linear Gaussian, right? And so now what we do is, instead of talking in terms of just the outputs that my model is making, we're going to talk in terms of output probabilities. So here we're going to denote that as p theta of y given x, okay? So that means given an input, right, I pass that through my model, I get an entire distribution of possible outputs, right? And this distribution is controlled by my parameters theta, which in this case is w and b, right? And here in this particular case for linear Gaussian, right, it would be, defined according to the Gaussian probability density, right? So here would be normal of y given my mean being wx plus b, and then sigma squared. Okay, you might notice that notationally, by the way, I used this squiggly n in two different ways, right? In the first way on top, it was used to define the actual distribution, the actual Gaussian distribution with the mean and the variance. And then on the bottom, this thing where I have, three things, right, is the probability value, right? The probability value under the Gaussian distribution of y if I have this mean and variance. Okay, so just a small notational note. Okay, so this is what a probabilistic model could look like. Now what I want to do is actually go back and talk a little bit about maximum likelihood estimation and how we're going to be thinking about it in this class. Okay. Before I do that, are there any questions so far about probabilistic models or the motivation behind MLE or anything else actually? Yeah, so the difference in notation, right? So you'll see I don't think, oh wait, I have a laser pointer. That should help. Okay, so this top thing, can you see that, my laser pointer? Cool, this top thing right here, okay? This is a distribution, right? It's a Gaussian distribution with a particular mean and a particular variance, okay? This thing down here, right? This is a number. It's actually a probability density, not a distribution, right? It is the probability of y given this particular mean and this particular variance for the Gaussian distribution. Is that a semicolon following the Y? This thing right here, this thing is a semicolon, yes. And usually things that follow semicolons in this type of notation are parameters. So what parameterizes your Gaussian? A mean and a variance, right? And so usually when you write it this way, you'll put the mean and the variance after the semicolon here. The black marker on the graph is representing the Gaussian distribution. Yes, that's right. It's my best attempt at drawing a Gaussian distribution. Okay, so I want to take a slight detour into a slide that you'll probably have a slightly better appreciation for after the week is done. But I'm putting it here so that hopefully you can even start thinking about it early. So we're talking about MLE, and eventually we're going to talk about MLE for machine learning. But really, it's good to know that MLE is it's a very general tool for statistical inference as a whole. It's probably the most widely used tool in statistical inference, period. And why is it relevant here? Well, it's relevant here because much of machine learning really is just statistical inference, right? We're given a bunch of data, and then we're trying to essentially infer, or what we call learn, right? What parameters best explain that data. That's a statistical inference problem, right? Not all of machine learning can be cast this way, but a huge chunk of it can. And that's why MLE is really relevant to machine learning. The key thing is that machine learning, right, is a little bit more specific. It's almost like a lot of machine learning can be thought of as a very specific form of statistical inference, where we care about models that go from inputs to outputs, instead of, for example, something like a population level model of the data, which is something that might be very relevant in many other types of statistical inference. And actually, later on in this lecture, we're going to start with an example that is actually, trying to infer parameters using MLE for a population level model. We also, in machine learning, we don't tend to think as hard about whether or not the model is misspecified, although maybe we should. So what does misspecified mean? Well, basically, you remember on a previous slide, I said that what we're going to do is we're going to assume that there's some setting of the parameters that actually generated our data, right? There's actually some linear relationship between my inputs and my outputs. And all I'm trying to do is sort of recover what that relationship is through this framework of MLE. Well, when I say misspecified, what that means is that the actual relationship that's encoded in my data, it does not actually reflect these modeling assumptions that I'm making. So maybe the relationship between inputs and outputs is not linear. Maybe it's actually like quadratic or something like that. Well, then if I were trying to fit or learn a linear model, that would obviously be a bad fit, right? And then in that case, we would call our model misspecified. So model misspecification can be a serious problem, right? If we're just trying to learn the wrong model on our data, then we might never get good performance. And this is a problem that people think about a lot, generally speaking, in other types of statistical inference, but it's not really something that we actually think a lot about in machine learning. Although maybe we should, because we in theory care equally as much if our model is misspecified. It's just not usually something that we put a lot of brain power towards. Okay, but anyway, we can revisit this slide at a later point, or maybe you can revisit this slide at a later point, and hopefully it'll be a little bit more clear. But first, let's actually dive into the actual math behind MLE, and then hopefully some of these things will really start clicking together. Some of the stuff on the previous slides will start clicking together. And again, we'll start with a non-machine learning overview of what MLE looks like, because it might actually be a little bit simpler to start from there. So what do I mean by non-machine learning? Well, forget about the whole input-output thing, all right? For now, let's just assume that we're given a bunch of data, and they're just X's, okay? They're just observations from some underlying data generating process that we don't get to observe. We only get, n observations sampled IID from our process, right? And we'll call that data set D, squiggly D, cursive D, right? Notice here that, these X's are now, in non-cursive and bold, which means that, they can be some n-dimensional vector, right? What we're going to do is that we're going to assume or, posit a set of distributions on X, right? And this is kind of, the model that we're going to put forward as to, I think that there is some model in this set that can explain my data. Generally, what does this look like? Oh, I'm still in laser point. Generally, what does this look like? Well, we have some set, right, of distributions parameterized by different values of theta, for theta in some family of parameters. What does that mean? Well, this capital theta here, right, for example, could be all the different possible values for W and B, right? Which would then mean that this set contains all possible linear, or all possible, and then with also like a sigma squared, then this set contains all possible linear Gaussian. Actually here we're talking about. So here we're actually not talking about inputs and outputs, right? So let's say that, for example, capital theta includes all the different possible values for a mean and a variance, a mu and a sigma squared for different Gaussian distributions, right? Well, then P theta would represent all different possible Gaussians, this set would represent all the different possible Gaussians that I could use to try to explain my data, right? And this is actually the actual example that we're going to be looking at after we pose some of these definitions. So I have this set of distributions that I'm throwing forward. And what I'm doing is I'm actually assuming that my data was sampled from some member of this set, some member of this distribution family. What does that mean? Well, it means that X1, here is capital, right? Because they're random variables, all the way through Xn, was IID sampled from some P theta hat. Okay, so for some theta hat in this family that I have here, okay? So what does this mean? Well, it means that there was actually, some setting of the parameters, right, that actually generated the data that I now have in my data set. There's some setting in these parameters, and then if this assumption actually holds, then what I can say is that my goal, right, is to essentially recover theta hat. That's kind of the thing that I want to be doing, right? But again, this is sort of like, we motivated from this direction, but are we actually really, do we actually really believe that there's a theta hat that can represent our data? Well, that depends on the application. And a lot of times in machine learning applications, we don't really believe or think about it too hard. But this is one way that we can sort of understand what maximum likelihood estimation is trying to do, is it's trying to recover the parameter settings that actually generated the data that we observed, okay? But a cleaner way to sort of, or a more concise way to write the objective or the definition of MLE is to essentially say that we're looking for the maximum likelihood estimate of our parameters, which I'll denote as theta MLE, and that is actually defined as the maximum over all possible parameters of whatever parameters maximize the probability of the data that I saw. That's my best attempt at drawing that cursive D, right? And this, based on the IID assumption that I have here, right, is equal to the maximum let me redraw that, make it a little bit cleaner. It's equal to the maximum of a product of individual data point probabilities, right? So P theta of xi. So that's the thing that I'm actually looking for. The maximum likelihood estimate of my parameters is whatever parameters maximize the probability of the data that I have actually observed. Okay, so I'll pause again here for questions. Now we've defined what MLE actually is, at least in this, particular basic non-machine learning setup, right? Where I don't have X's and Y's, I just have X's. But, the same concept will translate in a fairly straightforward way into the case where I have both inputs and outputs. But let's pause here for a second. And, I'll look through the chat for questions, but also, feel free to ask anything by unmuting yourself if you'd like.
Hey Marvin, can you explain the p theta again? Like, what does that mean?
P theta. Let me pull out my laser pointer again. You mean this part up here?
Yeah.
Right. So p theta, right? So this is a set, right? And the set varies over all the possible parameter values that I could have, right? So each member of this set is a distribution on the data. So think about, for example, if theta, big theta, capital theta over here included, all possible values for mean and variance of a Gaussian distribution, right? Then my p thetas would all be Gaussians, right? And then this set is the set of all possible Gaussian distributions. And then basically what I'd be saying here is that I assume that there's some Gaussian, right, some theta hat that actually generated the data that I saw. And then what I'm trying to do is find the Gaussian distribution or the parameters, the mean and variance for a Gaussian distribution that actually maximizes the probability of my observed data.
I see. Can I ask another question? Why do we use product for
product? Oh,
yeah.
So when x1 through xn are independent, right? Then the probability of x1 through xn is a product of their individual probabilities, right?
Okay. Yeah. Yes. All right, got it.
Thanks.
Thank you.
I'm sure there'll be more questions. So, also feel free to ask out loud, but I'm also just scanning through the chat. Are the x's random variables? Yes. What's the symbol within p theta in the objective? Oh, yes. If you're talking about this first one here, that's my best attempt at drawing this D, the probability of my data set. Can we get a concise explanation of MLE? Yeah, that is tricky, and I do apologize. The most concise way that I can probably say it is the maximum likelihood estimate are the parameters that maximize the likelihood of your observed data. So that's this thing down here, right? I think that's most concise because it actually tells you what it is that we're going to be trying to do. Is the set/family of distributions of all the same type? So that's a good question. That's up to the modeler, you, right? So maybe you say, well, all Gaussians seems like a reasonable bet, and then you start there. Or you could be a little bit, more general and include, members of a different type of family. It all depends on, the problem that you're working with and what assumptions you feel like are reasonable. Although a lot of the times for convenience and simplicity, we usually stick to, a particular type of distribution like all Gaussians or something like that. And why are we using Gaussian distributions? That was just an example. We don't necessarily need to use Gaussian distributions. Although the example that we're going to work on next actually is using Gaussian distributions.
Gaussian distribution is the same thing with a normal distribution?
Yes. Sorry, that circled H is a capital theta. Here we assume that x1 through xn are independent, and we don't know whether they're independent. Does it change anything? Yes, it changes a lot, because not having independent random variables is just a huge pain in the ass. And we'll see exactly why independence is useful. I think, one of the reasons why it's useful, approximately 2 slides from now. And if you don't have that, then things, generally speaking, get just a lot trickier mathematically to actually work out. Okay, let's get into an example. And the first example that we're going to do actually is for Gaussians. So maximum likelihood estimation for a univariate Gaussian. Univariate meaning in one dimension. So suppose that you were given a set of height measurements. So like you measure the height of everybody in this class or something like that. And you believe justifiably that actually the underlying distribution of heights within a particular population is Gaussian. People have actually done studies on this and shown that this is a pretty reasonable modeling assumption for something like height. Oftentimes we can model it pretty accurately as a Gaussian distribution with some mean and some variance, right? So the x1 to xn that we had on the previous slide, those are the numbers that were given for the different height measurements. So then the question is, how would you estimate the mean and the variance of this Gaussian corresponding to heights from the data, the measurements that you're given, right? Well, it turns out that the way that you're probably thinking of doing it intuitively corresponds to maximum likelihood estimation, and we're going to go through the math for why it corresponds to sort of this very intuitive answer. And this will be our first example of MLE in action. But this example isn't really a machine learning example. Can anyone tell me why, either out loud or in the chat?
Is it because it's calculus?
I'm sorry?
Is it because it's calculus?
It's because it's what?
Calculus.
I'm sorry. Maybe can you write down? I can't. Yeah, so I'm seeing a couple of different answers in the chat. Oh, calculus. I'm sorry. Calculus is okay. We like calculus. We're going to do a bunch of calculus in this class, also for machine learning. And it's also kind of okay to do things like brute force the answer for a certain definition of brute force. But I'm seeing that the most common answer that people are writing is that we are not predicting any sort of output given an input. So remember, that's the whole point of machine learning, right? It's to learn a model that can take some particular input, like your height, for example, and then be able to predict some output given that input. Like, for example, I don't know, your weight. I don't know if that's a good example, but it has to be predicting some kind of output given your input, right? We can't just be trying to learn what we would consider here to be essentially a population level model of the data, right? Give me the mean and the variance for the distribution of heights in this population. That's not a machine learning problem, because once I have that model, I'm not going to be using it for predicting on new anything, right? That's just a model that sort of tells me something about this population, but it doesn't work on an input-output level, so it's not really a machine learning example. And we'll do this first, but in the next lecture, we'll talk a little bit more about actual machine learning examples. Okay, so what are we doing here? Well, first, right, we're assuming that each data point was generated IID, independently and identically distributed, according to some Gaussian distribution that we don't know, right? So it has some mean mu hat and some variance sigma hat squared, right? But we just don't know what those values are. We only have the measurements, the x's that are given to us in this data set D, right? So D consists of x1 through xn, right? These are lowercase, right? Because they're actual numbers, they're measurements, observations that we've been given of heights. And we assume that they were drawn from, the same Gaussian distribution with parameters that we just don't know, right? So here, right, the parameters that I'm working with, theta, are going to be, the mean and the variance that actually parameterize my Gaussian distribution. And my goal, right, is to find the maximum likelihood estimates of these parameters which I could equivalently write separately as the MLE of my mean, and then the MLE of my variance, which equals the same thing that we had on the previous slide, right? The maximum over all possible parameters that I could specify of the product of the probabilities, the likelihoods of my data, right? And so here again, I'll use this N notation, the second one, right? Where I have the probability of some number xi under the Gaussian distribution specified by mu and sigma squared, okay? So that's the thing that we're looking for here. We're looking for the maximum likelihood estimate of my mean and my variance, which is, whatever mean and variance maximize the probability of my observed data. So how would I actually solve this optimization problem, this maximization? Well, the classic calculus way that we would do it, right, is we take the derivative of this and set it equal to 0, right? And if we weren't being lazy, we could also check the second derivatives and make sure that it satisfies those criteria to actually be a maximum, right, and not some other kind of stationary point. But doing this for a product of terms is actually really quite tricky and messy, right? And we're going to get some pretty nasty derivatives if we try to do this directly. So a key idea behind a lot of maximum likelihood estimation is to take the log, and you basically always do this, okay? You always take the log, okay? So log, right, is what's known as a monotonically increasing function, which means that it doesn't change my optimization problem. The max of a function, the argmax of a function is the same as the argmax of the log of that function, right? So that's why taking the log is going to be great because it doesn't change the problem, but it makes these products turn into sums, and then sums get a lot easier to work with when we're talking about derivatives, right? So log is a monotonically increasing function, which means that I have that the maximum that I had on the last slide, right, is the same as the argmax of the log of the same thing. Okay. Now, if I were to actually, be patient and actually write out what this whole thing is, right? Well, remember, a Gaussian distribution, it's what? It's, some 1 over, square root of 2 pi sigma squared times the exponent of, x minus mu squared over sigma squared, something along those lines, right? So if I take the log of that, right, then this product turns into a sum first, right? So I have, instead of a product over I, have a sum over I, right, of, this log of this Gaussian, which ends up looking something like this. I already wrote it out just for convenience, right? We end up having -1/2 xi minus mu squared over sigma squared -1/2 log sigma squared. And then something that I'll write here as C. So what is C? Well, C we'll usually use to denote a constant, which does not actually depend on either mu or sigma squared. So if something doesn't depend on mu or sigma squared, but that's the thing that I'm trying to maximize, then I can just get rid of it in my maximization problem, right? Because it doesn't change the resulting answer that I'm going to get, right? And so basically what this ends up looking like is we wish to find the argmax over mu and sigma squared of, just rearranging some of these terms, right? -1/2 sigma squared sum of I equals 1 to n xi minus mu squared plus this other term, right? This n over 2 log sigma squared term. And the way that we actually solve this is by taking partial derivatives and setting equal to 0, but I'm out of time, so I'll do that next time. So next time we'll see, the thrilling finale of how to do a maximum likelihood estimate for univariate Gaussian. There's another example in these slides, and I'll post the annotated version as well. There's another example of a multinomial distribution, which is also quite interesting, but we'll skip that one in the interest of time. So next time we'll finish this up, and then we'll talk about MLE for machine learning models. And just remember, I'm around for half an hour if anyone has any questions. Those are my office hours. All right, thank you, everyone.
Hey, mình